That's why it is mentioned the null hypothesis is nullifiable. We only test the null hypothesis, okay? And then if we can accept the null hypothesis, that is, we accept the existing facts. And then if we reject the null hypothesis, it means usually we accept the alternate hypothesis. So here, in case of the null hypothesis testing, we have two types of tests. One is called the parametric test, another one is called the non-parametric test. And what are the parametric tests? Like the G-test, T-test, F-test, ANOVA, those are the names of some parametric test. And what are the non-parametric tests? Like the chi-square test, U-test, and ACE-test. Those are actually called non-parametric tests. If we want to explain a little bit detail about the parametric and non-parametric tests, then parametric test, it means usually we applied under the circumstance where population is normally distributed. Okay, we assume that the population is normally distributed. If that is the case, then usually we apply the parametric test. In parametric test, we need the parameters, values of parameters like the mean, standard deviation. So those values usually we need in parametric test. And here is some of the examples of parametric test: T-test, G-test, F-test, ANOVA, Pearson coefficient, correlation test. All these are actually our parametric test. These are applied when data is quantitative. Okay, that means we can say we will apply the parametric test on quantitative data, and there are applied when the scale of measurement is either an interval or ratio scale. That means usually we use some sort of Likert scale to collect the data. Okay, so that's our in parametric test. But how about non-parametric test? In non-parametric test, usually the main consideration is whether your data is normally distributed or not. If the data is not normally distributed, some sort of skewed distribution is there, then you have to think about non-parametric test. Where parametric test cannot apply, and on that case also we have to consider non-parametric test. That means if we cannot apply the parametric test in some cases, then we have to apply the non-parametric test. These tests are also called distribution free test. Why? Because data is not normally distributed. Data is not normally distributed. And parameters like the mean, standard deviation, those are not also available. Okay, so that's why we need to maybe apply some sort of non-parametric test. Some examples like the chi-square test, U-test. U-test is name of the another name of U-test is Mann-Whitney test, and ACE-test, that is a Kruskal-Wills test, and Spearman's rank correlation test. All those are non-parametric tests. And these are applied where data is qualitative. Here you can see that the data are qualitative. So qualitative data, not the quantitative. Some interview or some like good, better, best, or some scale, the excellent, or maybe outstanding. So those are the quality. Okay, qualitative tests. These are applied where the scale of measurement is either an ordinal or maybe nominal scale. Okay, so we can apply the nominal scale or maybe ordinal scale to find out or to collect the data in case of our non-parametric test the data. And then here is the hypothesis. We know that the null hypothesis, usually it is called the educated guess about the population. That means what's the existing fact, already known fact, those are usually called the null hypothesis. And what we want to prove or what we want to establish, that usually we discussed or defined in our alternate hypothesis. That is a prediction of the relationship between two or more variables. So in null hypothesis, in this case null hypothesis, a statement which states that there is no relationship between variables. So that's there is no relationship between the variable. So that is the null hypothesis. That means that is the maybe the current fact or common belief. Okay. So that is our null hypothesis. But first, in alternate hypothesis, we have to state some relationships. We can assume or we can presume some of the relationship. A statement which states that there is a relationship between those variables. So those are usually defined in alternate hypothesis. For example, here you can see there is increase in number of cancer patients is not due to the increase of population level. This is common belief. That means maybe the population level increase, it doesn't mean that on that population cancer patient also increase. So that is the common belief. But if we can say that kind of a statement that the cancer patient is increased due to the increase of population level, then we have to prove it. Okay, we have to prove it, and that's in alternate hypothesis. That means this is our assumption. This is our assumption. So this assumption we have to place in alternate hypothesis. So usually the null hypothesis is defined by HO. That is, this is the symbolic representation. HO means that null hypothesis, and H1 or HA denoted by the alternate hypothesis. So it is also mentioned that it is exact opposite of what an investigator predicts or expects. Okay, exact opposite in null hypothesis. It is exactly what investigator predicts or maybe expects. It is a null hypothesis which is being tested. That means, as I already mentioned, that only null hypothesis is being tested. That means we can test, we can accept, or we can reject the null hypothesis only. And statistical tests are not performed on alternate hypothesis. That means when we will collect the data, we have to keep in mind that we want to prove the null hypothesis. Okay, null hypothesis, and then maybe we can say we need to we will accept or maybe reject the null hypothesis. If we reject the null hypothesis, it means we can accept the alternate hypothesis. The null hypothesis is either rejected or maybe not. For hypothesis testing, some of the terminologies are very important. We need to know those terminologies before going to discuss the test. One is called the confidence interval. Confidence interval, it means that how much uncertainty is there is with any particular statistic. Okay, any particular statistic. You can say that okay. You can say that okay, maybe there is 90% of the students of Brack University maybe will do better in future. Okay, so that means this is a statement, but to prove your statement, maybe you can collect also the data and you prove it. There is 90% of the students in future they will do better in their domain. You prove it, but again there is the how uncertain it is there in your statistic. When you say 90% of the students, maybe you collected the data, but there are some students actually those are not maybe not good enough, or we can say not do well in future. In your statistics, such type of statistics, such type of students may be there. So that's why you have to think about your confidence interval. That means when you say some statistics, then you have to think about the confidence interval for that. So it tells you the confidence you did. The results from the poll or maybe survey reflect what you would expect to find where possible to survey the entire population. It means maybe to prove any statistics, you will collect the data from the sample, not from the whole population. But when you say some statistical proof, it means that it will be applicable to the entire population or whole population. Okay, so that's why the confidence interval is there. That means your level of significance is there. That is how significant your statistics is, you have to say that. So that's why here it is another terminology that is related to your confidence interval is confidence level. Okay, confidence level. So confidence interval. Usually we measure the confidence interval, but it will also explain the confidence level. Usually the confidence level expressed as a percentage, like maybe 95% confidence level. When you say the statistics, you are 95% confident about that. What does it mean? It means that if you repeat the experiment or maybe survey again and again, then 95% of the time it will prove your statement, or it will justify your statement. So that is our 95% confidence interval, confidence level, 95% confidence level. That means 95% of the time your result will match the results you get from the population. However, the confidence interval are your results. Okay, so confidence interval are your results. That those are the value, not the percentage. So in this case, we can see that there is maybe if you can say that 95% confidence level I have, then that means your experiment will show 95% time the result you just mentioned. Okay, but what about the confidence interval there? That is that the result, the limit of your results. Maybe you can say that you have the upper limit and the lower limit. Okay, these are the limits of your result. These are the limits of your result. So it means the confidence interval, it will mention the level of your results, but confidence level, it will say the confidence level in percentage. For example, here it is an example, like US Census Bureau routinely uses confidence level of 90%. So 90% confidence level. Let's say the population in poverty in 1995 stated the confidence level 90%. For the statistics, the number of people in poverty in the United States is between this limit. So here this is the lower limit, this is the lower limit, and this is the upper limit for that. This is upper limit for that. So that means the result you will find between these two limits, that is lower limit and upper limit, 90% of the time. So that means 90% of the time you will get the result. You will get the result within this limit. So this limit, this is called the confidence interval, and this 90% is our confidence level. Okay, confidence level. That means sometimes you may get the number greater than the upper limit also. Sometimes maybe you will get the number of population in poverty level that is greater than 37 lakh, maybe 30, 38 something. Sometimes maybe you will get that result, but that is not maybe within 90%. Within 90%, maybe just 1% of the time you will get the result within the 38 lakhs plus. Okay, and that is not counted here. So that's why in confidence interval you will find out the lower limit and upper limit, and you have to mention the confidence level for that. That is how much confident you are that the result will be between these two limits, upper limit and lower limit. So how to determine the confidence interval? Many times actually we have to determine the confidence interval, like maybe in case of the data science and machine learning, some of the models you have applied to a data set, and then you claim that that is my model, that the proposed model accuracy is maybe 95%. Okay, you just mentioned that is your that is the your accuracy of your model is 95%. So what does it mean? That means the 95%, if you run the program again and again for different set of data and different set of seeds, you will not get always the 95% accuracy. Okay, so sometimes maybe your accuracy will be like a little bit higher, like maybe 95.7%, and sometimes you will get the result maybe even 92.3%. Okay, so sometimes you will get the result even maybe you can say 98%. Sometimes maybe you will get the result like 91%. Okay, so in your different run, different values will show. Okay, it can vary, maybe like sometimes 91%, sometimes 98%. But if you claim that is your result is 95%, it means that on that case you have to think about the confidence interval for that. The confidence interval, it means 95% plus minus something you have to add here. Okay, that is the SE, that is the some kind of error you have. So on that case, maybe you can say that the result will vary within 92 to 96, within this interval. Like sometimes 92%, sometimes 96%. So you can define that this is lower limit, and you can define that this is upper limit. And then you can define that, okay, maybe 99% of the time, you will get the result within this limit. Okay, so that means how much time maybe you will run that model, and then at 99% of the time your result will vary within 92 to 96%. Sometimes you will get 98%, but maybe that is within the 1%. Okay, within the 1%. Sometimes maybe you will get the 91% also. That is also 1% of the time. Okay, but 99% of the time you will get the result 92 to 96%. Okay, so that's why the confidence interval, mentioning confidence interval is necessary. That means finding out the lower limit and upper limit, and then telling the confidence level is necessary for the statistical presentation of your result. Let's say here it is mentioned that a group of 10 foot surgery patients had a mean weight of 240 pounds, and the sample standard deviation is 25 pounds. Then find out the confidence interval for the sample of true mean weight of all foot surgery patients. So you have to use 95% confidence level. So if this is the case, then to find out the confidence interval, usually we use these equations. This is one equation, and this is another equation. Here it is called the T. Here this is the G. There is the T score and G score. So that means we have to. You can apply either T distribution or maybe we can apply G distribution. But which one we have to use? At first, we need to know that. So at first, from your description, you have to identify that. Do you know the population standard deviation? That is the sigma. So whether you know the sigma or not. The population standard deviation, and this is our sample standard deviation. S is our sample standard deviation. The population standard deviation, and S is called the sample standard deviation. Do we know the population standard deviation? So in this description, we can see that the sample standard deviation was 25 pounds. That means we don't know the population. We don't know only the sample. So that's why if yes, that is, if you know that is the population standard deviation, then go in this direction. Otherwise, go in this direction. So that means we know the sample standard deviation, not the population. So use the t-score, use the t-test to find out the confidence interval. Okay. So if we somehow we know that the sigma, then is the sample size above 30, above above or equal 30? Okay, above or equal 30, above or equal 30 actually. If it is above or equal 30, if yes, then use the g-score. Otherwise, we have to use the t-score. Okay, so that means if the sample size is greater than or equal 30, then we have to use the g-score. Otherwise, we have to use the t-score. Usually, greater than or equal 30, greater than or equal 30, usually call this one as the larger sample size, and below the 30 is called a smaller sample size. Okay. So if greater than or equal 30, then you have to apply g-score. Otherwise, we have to apply t-score. How many samples we have? The group of 10 foot surgery patients. That means we have collected the data only from the 10 patients, and so it is below 30. Okay, below 30. And if it is below 30, then again it is mentioned that you have to apply t-score. Okay, you have to apply the t-score. Okay, then how can we determine that? The first step is subtract 1 from the sample size to find out the degree of freedom. Degree of freedom. Subtract 1 from the sample size to find out the degree of freedom. So sample size, we have 10 foot surgery patients. 10 foot surgery patients. So the degree of freedom will be sample size minus 1. Okay, so that is the 9. Why it is degree of freedom? Because we can see that so if you know the average, the average value, okay, the mean value, and if you know the results, the maybe average weight. If you know the average weight, like average weight, the mean weight, and the mean weight, we know the mean weight. And if you know the weight of 9 samples, then we can find out the weight of 10th sample. Okay, 10th sample, the 10th sample. You can find out the weight of the 10th sample. So that means we need the 9. We need the 9. So degree of freedom is 9 here. Okay, degree of freedom is 9. So 10 minus 1 is 9. So subtract 1 from the sample size, we will get the degree of freedom, that is 9. And subtract the confidence level 1 from 1, then divide by 2. Okay, to find out the alpha. This is called the alpha, the significance level. So 1 minus 0.95, because we can see we have, it is mentioned about the 95% confidence level. Okay, 95% confidence level. So 1 minus 95, that is 0.95 divided by 2. So you will get 0.25. Okay, 0.25. So you will get 0.25. You can see that there is the alpha is significance level. So the significance level both sides. So this side and also this side. So that's why we divide the significance level 0.5 divided by 2. Okay, so that means 1 minus 95, it is 0.5. So it will be 0.05. So 0.05 divided by 2. Okay, divided by 2. So it will be 0.025. That is alpha will be 0.025. And then look up your answer to step 1 and 2 in T distribution table. That means we have to use the T table. The T table, this is one of the standard table for the statistics. Okay, from that T table we will find out the value of our T. T distribution, this T. Okay. And for that, what we need the degree of freedom, like here, if we can see our statistical table. We need the T table. Degree of freedom is what? Degree of freedom is, in our case, it is 9. So degree of freedom is 9. And then we need to find out that it's T alpha. Alpha is 0.05. So here the T, and then alpha is 0.025. So 0.025 is this. This is the value. 2.262. This is the value, 2.262. So here we got, using the degree of freedom and using the alpha, we got the T alpha is 2.262. 2.262. Then find out the standard error. The standard error is, it is the sample standard deviation divided by square root of n. And that is this part, actually. This is the part. This is called a standard error, SE. Okay, SE. So a standard error. The standard error is, in this case, we can see here, it is the sample standard deviation is given. It is 25 pound. Okay, so here is the 25. And then n is the sample size. In our case, the sample size is 10 foot surgery patients, that is n equal 10. So here is n equal 10. Then we can see it is 7.90. Okay, 7.90. The standard error is 7.90. And then we have to compute this part. This part, actually, it is T times S by square root of n. So S by square root of n, that is a standard error. So we have to multiply a standard error by T. So here the T we have already determined. The T we have already determined. The T score we have already determined. The T score times our standard error. Then here is the 17. Okay. So that means x bar plus minus 17.88. 17.88. So now we have to find out the lower limit and upper limit. So x bar, that is the mean value. We can calculate mean, or maybe if it is given, then directly we can use. So a group of 10 surgery patients had mean weight of 240 pound. Okay, mean weight is given 240. So here is the 240. 240 minus 17.88 will give us the lower limit. So this is the lower bound or lower limit. And 240 plus 17.88 will give us the upper limit. Okay, 257.883. Okay, so this is our upper limit. So now we can see that our confidence interval here is 222.117 to 257.883. So this will be our confidence interval, and we assuming confidence level is 95%. Okay, 95%. So this is how we can determine the confidence interval with the help of our given data and also confidence level. Okay, confidence. Now I want to discuss some of our parametric and non-parametric tests. At first, the parametric test. So in our last class, we have discussed this. So here is this. So it is mentioned that blood glucose level for obese patients have a mean of 100 with a standard deviation of 15. With a standard deviation of 15. A researcher thinks that a diet with high raw cornstarch will have a positive or negative effect on blood glucose levels. So positive or negative effect. It means blood glucose level may increase or blood glucose level may decrease. Okay. So that means the blood glucose level, we can see the blood glucose level for obese patients, they have the mean is 100. So if they take the meal with high raw cornstarch, then the glucose level may increase. It can be maybe 110 or maybe decrease, like it can be maybe the 80 or 90. Okay, so for that, to prove this hypothesis, this assumption, a sample of 30 patients who had tried the raw cornstarch. Okay, so 30 patients who have tried raw cornstarch diet have a mean glucose level of 140. Okay, so here you can see that is the 30 patients have taken maybe for the experiment, and then we observe that the mean glucose level it was like 140. Yes, the hypothesis that the raw cornstarch had an effect. Okay, raw cornstarch had an effect. That means generally we can assume that okay, the raw cornstarch don't have any impact on the that is obese patient with blood glucose level. But we can the researcher mentioned that assume that if those patients consume, that is the raw cornstarch, then maybe their glucose level can increase or maybe can decrease. Okay, there is some effect is there. So for that case, at first we have to determine the null hypothesis. The null hypothesis here is the blood glucose level for obese patient has a mean 100. Okay, so that's why we can see H0, there is the mu is 100. Mu is 100. So mu is 100. So that means that the parameter is there, mean is there. Okay, mean is there. So it's kind of the parametric test we can apply. So mean is there. So mu is 100. And what will be the alternate hypothesis? The alternate hypothesis, it is mentioned that it may have the positive or negative impact, or maybe it can be increased or not increased. So that means it is mu is not equal 100. Mu is not equal. That is the in alternate hypothesis. The mu is not equal 0. Sorry, not equal 100. It means it can be greater than 100 or it can be less than 100. Okay, less than 100. So now we want to test this hypothesis. But at first we need to determine that is which kind of test we need to apply. Okay, we need to apply. Then here is we can see this one. We have to apply the parametric test, but which parametric test? G or T. So it is mentioned that t-test is used when the sample size is small and the population variance is not known. Population variance is not known. So z-test is when z-test is used, the sample size is large and the population variance is known. The population variance is known. The population variance actually the sigma. Okay, that is sigma. So if sigma is known, then we have to use z-test. If the sample size is large, we have to use z-test. Otherwise, we have to use the t-test. Okay. So the sample size large, it means that is the population size is greater than or equal 30. Okay? The population size population size is greater than or equal 30. So that is called the large. Usually we assume that the large. Okay. So now we can see here, in this case, whether we know the sigma or not. We can see that there is with a standard deviation of 15, okay, blood glucose level, patients. This is not the sample standard deviation. So this is population standard deviation. That means sigma is given here. So we know the sigma, and there is 15. And how about our sample? The sample of 30 patients. Okay, 30 patients. The 30 or greater than that. The 30 or greater than that is usually we call it the large. So that means we can apply G test. G test. Then for the G test, what will be the G test value or the G score? The equation is here. This is the equation for that. So what are the steps? The steps is state the null hypothesis first. So we have already stated the null hypothesis. Then state the alternate hypothesis. Okay, so we have stated the alternate hypothesis. Then state the alpha level. Okay, and the alpha level, that is the significance level of your test. So here alpha, we assume that alpha is 0.05. Alpha is 0.05. This is actually user defined. You can define it like 0.05, 0.01, or maybe 0.001. So those are the significance level of alpha. So we will discuss a little more about the alpha after a few slides. So here is the significance level testing like 0.05. Okay, 0.05. That is 5%. And now find the rejection area from G table. So that means we have to find out the rejection area, or we can say we have to find out the G score, okay, from the G table, from the standard table given by the statistician, G table. But for that, what we need here, we have to find out the G score or G critical value, or we can say from the G table. So we have to find out that. On that case, you can see there is, if we think about our the data is normally distributed, because we know that is we are going to apply the parametric test. Okay, parametric test, we have known parameters of mean and also standard deviation, and we now we can assume that data is normally distributed. Okay, data is normally distributed. So here data is normally distributed. Then we can see that is and for that we know if data is normally distributed, then we will get the 50% data in our left side and 50% in our right side. 50% in our left side, right side. And then this is whether this one is one tail test or two tail test, we have to determine that. Based on our alternate hypothesis, we can see that is the mu, it can be greater than 100 or less than 100. Greater than 100 or less than 100. That means two conditions are there. It is less than, it is greater than. So that means it's kind of the two, it has two tail. Okay, it has two tail. There is less than means in this side, and greater than it means in this side. Okay, greater than means in this side. This is, if this is the mean, we have the mean. So greater than the mean and less than the mean. Okay, then it is a two tail test. So what we have to do, we have to divide this alpha by 2. So alpha is 0.05. 0.05, that is the 5%. That is the 5%, or 0.05. That is the 5%. That is, we have to divide it by 2. So 2, if we divide it by 2, then we will get what? We will get 2.5%. 2.5%. So that means the significance level it will be distributed in two sides. The amount is 2.5%. Okay. So now we can see that is the 50% minus 2.5%. So it is 47.5%. 47.5%. 47.5%. So here is the 47. We can say this is the 47.5%. So up to 47.5%. Or we can say this is actually 0.475. 0.475. Within this area, that means within that is 0.475 or within 47.5%, those are actually, you can say, true cases, and beyond that, those are kind of the false cases. Okay, those are false cases. So that's why we have to find out the G-score for that. The G-score for that using the table. So we have already determined these values, and now we want to apply. We want to find out the G-score here in two-tailed test. G-score in two-tailed test. Two-tailed test here. The table. Okay. We need to find out the value that is 0.475. Okay. That is 47.5%. Find out that value. We can see here 475. And this is the case. Okay. So this is 0.475. And for that, the G value or G score value is 1.9 here. And in column, 0.06. So that is 1.9 plus the column value is 0.06. 0.06. So it is 1.96. So this is the G score. This is the value of G score. G score. This is the value of G score. So here the G score, the value of G score is 1.96. Okay. So 1.96. You can see this is 1.96. G score value is 1.96. Similarly, for the other side, that is the negative side, you can say the score value, you will get the negative 1.96. So positive 1.96 to negative 1.96. So beyond that, those are our rejection zone. Those are our rejection zone. Beyond that, beyond this value, those are our rejection zone. So that means the acceptance zone is within 1.96, and then the rejection zone is beyond that. Beyond that, the rejection zone. So we already got the Z score. That is, we can say that it is actually within 1.96 standard deviation, positive and negative standard deviation. We will get the acceptance zone, and then beyond that, and the rejection zone. Okay, rejection. Now we have to find out our statistics. That is what we got from our data. So that is called the G statistics. So for finding out the G statistics, the G is x bar minus mu 0 divided by sigma by square root of n. Okay, so x bar. So the data in this case, we got the mean glucose level is 140. So here's the 140. And mu 0 is our 100. The mu 0 is 100. Okay, so this is our mean blood glucose level obese patients than normally. Okay, and this is from our observed data. and divided by the sigma. Sigma is given, the standard deviation sigma is 15, and divided by square root of n. N is the number of samples. Number of samples in this case 30. So here's the 30. So if we do the math, then we will get this 14.6. So 14.6 it means the 14.6 is here. Okay, maybe 14.6. That is 14.6 standard deviation. Okay, based on the data, actually we got it is in 14.6 standard deviation. So that is in rejection zone. Rejection zone. So what does it mean? It means that we can reject our null hypothesis. So reject our null hypothesis. So in our hypothesis, that is, we can reject the null hypothesis. So in reject the null hypothesis, it means we have to accept the alternate hypothesis. It means the researcher, whatever researcher thought, whatever researcher assume, that is the diet with high raw corner stress will have a positive or maybe negative effect on blood glucose level. This is correct. This one is correct. That is, his assumption is correct. Okay, so this is one of the G test. Now, another example is here. A principal at a certain school claims that the students in this school are above average intelligence. Okay, a random sample of 30 students, IQ score have the mean score of 1, 1, 2. Is there sufficient evidence to support the principal's claim? The mean population IQ is 100, with a standard deviation is 15. So these are the data given. Then we have to test whether the principal's claim is true or false. That is, his student or her students are above average intelligence. Okay, above average intelligence. Whether this claim is true or false, can we test the hypothesis here? And again, we can see that is some values are given, like mean IQ score, and then population IQ score, mean of that, the standard deviation of population, those are given. So that means we can apply the parametric hypothesis testing here. It means we can apply G or T test. And now we can see that is whether this standard deviation 15, this is the population, that means sigma is given. So that means we can say that sigma is 15 here. So we can apply the G test. And another one is how about the number of population? In this case, 30 students. Okay, 30 students. Again, the n is 30. So that is also statistically we can say that is large one. Okay, so we can apply G test again. So formula for the G statistics test is this one. Okay, this one. So we have to apply again. At first, we have to find out the null hypothesis, then alternate hypothesis. What will be the null hypothesis in that case? The mean population IQ score is 100. Okay, mean population IQ score is 100. So we can define that the null hypothesis, that is the mean, is 100. And then the claim of our principal is the above average intelligence. Above average intelligence, it means the mu is greater than 100. Okay, mu is greater than 100. So that is called the above average intelligence. That is greater than the mean. So alternate hypothesis is this. That is his or her students are above average intelligence. Okay. So can we test that hypothesis now? So we have tested the null hypothesis. We have tested the alternate hypothesis. We can assume that that state of alpha level. Again, we can assume that alpha is 0.05 in that case. 0.05. Okay, significance level. And then find the rejection area from the G table. Now we have to consider whether we have to apply the two-tailed test or maybe one-tailed test. And in this case, we can see the mean is greater than 100. Greater than 100, it means if the population is normally distributed like this, then we can say in this case it is greater than 100. That means it will be in this side, okay, greater than 100, not in this side or not in left side. So that means it is one tail test. So in one tail test, the 0.05, it means maybe you can say we need to find out the G score, and here is 0.05. That means 1 minus 0.05. Okay, so it is 0.95. Okay? 0.95. So it will be 0.95 here. That is the acceptance zone. 0.95, the acceptance zone. So we need to find out this value here in G table. Okay, in G table, to find out the rejection area. That means we have to find out the G score, or we have to find out the G critical value, and then beyond that, that will be our rejection zone. So from the G table, what we need to find out, and this time we can say one tail, G table of one tail, G table. So G table one tail. So in which tail? It is in left side or maybe right side. You can see these are the statistics for the left side, the table entry. This is the left side, but we have greater than. That means we have to think about like this one. Okay, this one is right side. So in our case, we have to find out 0.95. So we can see here, this is the 95, 0.95, 0.5, 9515. No, actually, directly we cannot get the 0.95, but the 0.95 will be between these two values. Okay, between these two values. 0.9495 to 9505, between these two values. So there is 1.6 here, 1.6 plus 0.04, that is 0.04 plus something. That is, we have to add something, because maybe the 0.95 we will get here at this point, maybe at this point. So it will be between these two values. That means it will be between these two values. T alpha will be between these two values. So greater than 0.0. So you can find out that value using the regression mechanism. Okay, regression mechanism, that is for how much difference here, how much difference in our alpha value. So then for the difference here, that means we can say 4595, and here is 9505. So for like in this case, the difference is 0.9505 minus of 0.9495. Okay, what's the difference? The 0 and then 1, then 0 and then 0. Okay, this is the difference between these two values. And how about the difference in alpha values? The difference in alpha values are 0.05 minus 0.04. So here is also the difference is 0.1. That means for this much difference, the difference in alpha value is 0.01. Then we have the 0.95, and our lower value here is 0.9495. How much difference is here? 5 and 5 is 5. Then 10 is 0. Here is a 0 and 0. Okay. So for this much difference, difference in alpha value is 0.01. Then for this difference, what will be the difference of for this much difference? What will be the difference in alpha value? Okay, what will be the difference in alpha value? We can easily find out that using the regression. So for that, you will get maybe the difference you will get 0.005. And if you add all this, then it is 1.6, then 4 and 5. Okay, 1.645. So this is the critical value of G or G score. So G score is this. Okay, 1.645. So this will be our G score. So that means greater than that is our rejection zone. Now what we have to do, we have to find out our value. That is our G statistics. So here is called the find out the test statistics. So we have to find out the G statistics. So in case of if we want to find out the G statistics, in this case, apply this equation. So x bar minus of mu 0 divided by sigma divided by square root of n. So x bar, first the value of that is 112, then 112. Okay, it will be 112, not the 112.5, minus our mu is 100. Here is the 100, and then divided by standard deviation is 15. Here is the 15, and the 30 is the number of students. So 30 is the number of students, and we can see it is 4.56. Okay, 4.56. So 4.56, and this score is 1.645. So this value actually greater than the 1.645. So that means it is in rejection zone. So if it is in rejection zone, it means we can reject again the null hypothesis. So if we reject the null hypothesis, it means we have to accept the professor's claim. Okay, the principal's claim. The principal said that his or her students are above average intelligent. That is true. The fact is true. Okay. So this is our non-parametric test. And now I think we can discuss about one non-parametric test. Okay, the chi-square test. The chi-square test. So chi-square test. This is as I already mentioned that this is our non-parametric test. Okay, so we have already mentioned that the chi-square is non-parametric. What we want to test here? The zodiac signs. Okay, maybe. Okay. Someone claimed that is the visual artists are actually from Aquarius or maybe from Capricorn zodiac sign. If you see some of the visual artists, then they are most likely from the zodiac sign Aquarius and Capricorn. So someone claimed this claim. That is, the zodiac signs, specifically visual. If you want to be visual artist, then you have to be with these two groups of zodiac signs. So someone claimed this. Then what will be the common fact or common belief? The common belief is this: that is, the zodiac signs are evenly distributed across the visual artist. Even visual artists are not from the specific group of zodiac signs. Okay, so that is our hypothesis. That is a null hypothesis, that zodiac signs are evenly distributed across visual artists. But the alternate hypothesis is this: that is, zodiac signs are not evenly distributed across visual artists. The visual artists are specifically from Aquarius and Capricorn, these two groups. Okay. So based on this someone's claim, we want to prove that whether that is the hypothesis, this null hypothesis, the null hypothesis is true or maybe false. And for that purpose, we have collected the data of 256 visual artists. 256 visual artists, we found that out of the 256 visual artists, 29 are from Aries and 24 are from Taurus and 22 from Gemini, 19 from Cancer and 21 from Leo and 18 from Virgo. Okay, so that means we have collected the data of 256 visual artists and we got different results. Then now we want to test the hypothesis. As we can see, that is this data actually, the zodiac signs are evenly distributed across visual artists. So here is we can see that there is no mean or something here. Okay, so this is just only the statement: zodiac signs are evenly distributed across visual artists, zodiac signs are not evenly distributed. So kind of the statements are there. So it means we have to think about non-parametric tests here. Okay. And for that, we can see here the data, the category. So we want to apply the chi-square or chi-square test. So these are the zodiac signs, total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, total 12 zodiac signs. And out of our 256 visual artists, we observed that 29 from Aries and 24 from Taurus, and then 22 from Gemini and 19 from Cancer. Okay, so these are our observations. Then what we have to do, we want to apply the chi-square test, and this is the equation for the chi-square test. This is chi-square. Chi-square equals summation of OI minus of EI. So OI, this is the observation, and EI is the expected number of observations. Expected number of observations. So we have to compute the expected number of observations here. There is the expected number. We can see 256 total subject, and we have total 12 zodiac signs. 256 by 12, if we divide, that is the expected number of observations from each and every zodiac signs. Okay, it is 21.33. 21.33, and that's what it is written. The expected number is actually 21. Here is the 21, 21, 21, 21. Okay, expected number is the same. Then OI minus of EI, that is observation minus expectation. Here observation is 29, and expectation is 21. What's the difference? Difference is 7.67. And then square of that is 58. Okay, then we have to divide it by expected I. So that means we have to divide it by 21.33. Then we will get 2.755. Similarly, for Taurus, it is 24. 24 minus 21, it is 2.66. And then a square of that, it will be 7.11. And then divide that the value by 21.33, you will get 0.33. Similarly, for Gemini, Cancer, all these for 12 zodiac signs, then we will get this. Okay, if we sum up those values, then we will get the chi-square. Okay, so this is the chi-square value. Chi-square value is 5.09. 5.09. This is the chi-square value. Now we have to find out this is our chi-square statistics. Okay, this is called chi-square statistics. That means from our data set we got the statistics, that is the chi-square statistics. Chi-square statistics, it is 5.09. but now what we have to do, we have to check our chi-square TTL value or chi-square tabular value or chi-square scores. Okay, and for that what we have to do, we have to find out again the degree of freedom. The degree of freedom is in this case we can see that is degree of freedom is total 12 minus of 1, so that is our 11. Okay, so 12 groups, out of that 12 minus 1 is the degree of freedom 11. So degree of freedom 11, degree of freedom 11. So we can see here the 11 is this, 11 is this, and then our value is 5.09. 5.09. So we have to find out the 5.09 here. So we can see that actually exact the value of 5.09 is not here. So we can find out the range. Within this range we will get the 5.09, and the corresponding p value, that is the p value is here, is given here, chi-square 0.9. So that means the corresponding p value is 0.950 to it is 0.900. So that means from 0.9 to 0.95 within this range. So our p value will be within this range. Within this range, it can be 0.92, it can be 0.93, like this way. Okay, within this range. But whether the the p value 0.9, like point greater than 0.9, is it significant or not? Significant or not? Okay. So we can see that is the p value. If the p value is greater than 0.1, it is not significant. In our case, p value is greater than 0.9. Greater than 0.9. Even p value greater than 0.1 is not significant, but less than 0.1 or less than 0.05 and less than 0.01, those are actually significant level. So it is marginally significant, significant, and highly significant. But in our case, p value is greater than 0.9. It means that it is not significant. So, it is not significant. So not significant means we should not reject our null hypothesis. Okay, so that is we should not reject our null hypothesis. So that means the alternate hypothesis should be rejected. If we should not reject the null hypothesis or alternate hypothesis, so the people null hypothesis should not be rejected. Okay, null hypothesis should not be rejected. So our null hypothesis is this: that is, zodiac signs are evenly distributed across the visual artist. So this statement should not be rejected. So if we reject this one, then we have to accept H1. But as from our statistics, we should not reject the H0. That means zodiac signs are evenly distributed across the visual artist. We should not reject this statement. That means we can say that the null hypothesis is true. Okay, null hypothesis is acceptable. So the zodiac signs are evenly distributed across the visual artist. That means not the visual artists are from the Aquarius and Capricorn group. Okay. Then the next, another thing, there is another chi-square example. So another hypothesis we can test, like someone mentioned that there is a significant relation between the marital status and education qualification. Okay, so marital status and education qualification. Someone is there is a significant relation between marital status and educational qualification. Someone assumed that. Okay, so that's why we put that one in alternate hypothesis. But in null hypothesis, we can see that there is no relation between marital status and educational qualification. So this is, maybe you can say, common belief. But someone want to prove that there is significant relation between marital status and education qualification. And for that, we have collected the data of different levels of students and their status, marital status. So we have collected data from 300 students of different levels, like middle school, high school, bachelor, master, PhD. And the marital status is never married, married, divorced, widow. Okay? So now we can see from our statistics, we have collected the data, and these are the collected data. So these are the collected data. But if we want to apply the chi-square test, we have to find out the expected number of observations. So these are the true observations. These are the true observations. Then what will be the expected number of observations? Like what will be the expected number of observations of never married people in middle school? What will be the expected number of observations? On that case, it will be there is never married people total. How many? It is total 90. And how many total in from middle school? It is maybe 39. So we have to multiply 90, then 39 divided by total. That is 30, 300. So here is this, the 90 times. So here is the 90 times 39 divided by 300. So we will get the expected number of observations. Similarly, for high school, it will be 90 times, here is the 90 divided by 300. So 90 times 90 divided by 300. So that is our expected number of observations. So we will find out the expected number of observations. Okay, here, expected number of observations. Now, what we have to do, we have to find out the chi-square, the chi-square value, that is our calculated value. So if we apply our equation, then we will get the chi-square value 23.57. Okay, 23.57. Now, if we want to test this hypothesis, whether it is true or false, maybe on that case, we need to find out, define the alpha. Maybe you can say alpha is 0.05, the significance level. Using this alpha and there is the degree of freedom. So degree of freedom, what will be the degree of freedom in this case? The degree of freedom will be columns -1, rows -1. That means the types of our schools, we can say 1, 2, 3, 4, 5. So 5 minus 1, and types of marital status 1, 2, 3, 4. 4 minus 1 is 3. Okay, so 4 times 3 is 12. So we will get 12. 12 is our degree of freedom. 12 is our degree of freedom, and significance is 0.05. Okay, so we have to find out this from chi-square table, from the chi-square table. What is the chi-square? Okay, here. From the chi-square table, you can say degree of freedom. We have 12. 12. That is 12 is our degree of freedom. Degree of freedom is 12. And then 0.25 or 0.5, 0.5, yeah. And the alpha, we assume the 0.5. And we can see that this value is 21.026. Okay, this is the chi-square statistic. So chi-square score, or we can say chi-square tabular value. Okay, 21.03. So now we can see that is the so this is the significant. This is our score. Okay, chi-square score. Chi-square score is 21.03, and we can say calculated value is greater than that. So that means the accepted region is up to this. Beyond that is our rejection zone. So we got the value beyond our accepted score, or critical score, critical value, chi-square critical value, beyond the chi-square critical value. It means we have to reject. We have to reject the null hypothesis. So that's why we reject the null hypothesis. Reject the null hypothesis, it means we have to reject the null hypothesis. It means there is no relation between marital status and education qualification. We have to reject this statement. It means that we have to accept the alternate hypothesis. There is significant relation between marital status and educational qualification. So this is the true fact. So we have to accept it. Okay. So this is how we can test also. We can test hypothesis using non-parametric test. So I think we have to stop here in today's lecture. That's all from our inferential statistics. So any question from your side? Anyone have any issue?
স্যার ফাইনালসের জন্য কি মিডের টপিকসগুলো ইনক্লুডেড থাকবে?
না, মিডের টপিকস ইনক্লুডেড থাকবে না।
ওকে
মিডের পরে যেটা শুধু সেটাই সিলেবাস।
ওকে
I think maybe this one is our last class. That is, I think we will not extend our syllabus anymore. In our next class, or maybe next to next class, maybe we have to take your presentation about the projects or the project demonstration, maybe.
আর তো ক্লাস হবে না জানি স্যার।
হ্যাঁ, স্যাটারডেতে হচ্ছে একটা ক্লাস হতে পারে।
স্যার আমার সানডেতে 421 এক্সাম আছে স্যার। সো
ঠিক আছে, এটা যদি না নিতে পারতাম তো বেটার হতো, কিন্তু হচ্ছে আমাদেরকে নিতে হবে। যাদের এক্সাম আছে বাই টাইপের, তারা শুরুতেই হচ্ছে তোমাদের প্রজেক্ট যেটা সেটা ডেমনস্ট্রেট করবে।
প্রজেক্ট নিয়ে একটু ডিটেইলস বললে ভালো হয়, কিভাবে ডেমনস্ট্রেট করব বা কি কি জিনিস রাখা লাগবে।
আচ্ছা, এখানে প্রজেক্ট যেটা সেটা ডেভেলপ, এটা তো অলরেডি তোমরা হচ্ছে তোমাদের কোনটার উপর প্রজেক্ট করবা সেটা সবাই গ্রুপ করে দিয়ে দিছো আর কি। তো সেখানে আমরা যেটা এক্সপেক্ট করি সেটা হচ্ছে ডেটা প্রসেসিং স্টেপ থেকে শুরু করে মডেলিং স্টেপ পর্যন্ত সবগুলা হচ্ছে তোমরা দেখাবো আর কি। এরকম না যে ডেটা কোনো প্রি প্রসেসিং ছাড়াই সরাসরি তোমরা মডেলিং চলে গেল, এরকম না যেন।
স্যার প্রেজেন্টেশনটা কি থার্সডেতে হবে না স্যাটারডেতে?
থার্সডেতে যদি এরকম হয় যে থার্সডেতে সম্ভবত সানডের স্কেডিউলটা ফলো করে, তাহলে তো আর আমরা থার্সডেতে করতে পারতেছি না, ঠিক না?
স্যাটারডে তো ঝামেলা হয়ে যাবে, এটাই তো সমস্যা।
স্যার সানডেতে স্যার দুইটা ফাইনাল এক্সাম আছে আমার।
অনেক ফাইনাল এক্সাম স্যার, এটা অনেক প্রবলেম।
বলো একটা স্কেজুল বলো তাহলে, পরপর 2টা ক্লাস যদি আমরা মিস করি তাহলে তো হয় না, ঠিক না? ইদার থার্সডে যদি থাকতো তাহলে থার্সডেতেই নেওয়া যেত আমরা, কিন্তু স্যাটারডে তো এখন ফ্রি করে দিতাম আমরা, ঠিক না?
17 স্যার এমনিও ক্লাস নেওয়া যাবে না মেবি স্যার, এক্সামের জন্য যে রিসেস দেওয়া হয় স্যার, সেই জন্য বন্ধ থাকার কথা।
হ্যাঁ হ্যাঁ, একদিন বন্ধ থাকার কথা, মানে এই এক্সামের আগের দিন।
2 দিন বন্ধ থাকে ফাইনালের সময় স্যার, মানে নিউ রুলস আর কি স্যার, এটা এই সেমিস্টার থেকে করতেছে।
তাই?
ফ্রাইডে স্যাটারডে বন্ধ, হ্যাঁ।
স্যার
আচ্ছা,
অনলাইনে
তাহলে
নেওয়া
আমরা
যায়
থার্সডে
প্রেজেন্টেশনটা, অথবা আমরা
প্রেজেন্টেশন অনলাইনে নিব, হ্যাঁ অনলাইনে নিব, কিন্তু ডেটটা কি হবে? থার্সডেতে রাতে করতে চাও?
জি স্যার, অনেক ভালো হয় তাহলে।
তাহলে স্যার থার্সডে রাতে করলেই ভালো হয় স্যার, প্রেজেন্টেশন যদি
ওকে
থাকে।
ওকে ওকে, ঠিক আছে, তাহলে ওভাবেই প্রিপারেশন নাও, আমি
স্যার
এটা
2 দিন
announce করে দেব।
স্লট রাখলে আই গেস বেটার হয়, কারণ একদিনে তো অনেক প্রেসার পড়ে যাবে।
আহ, আমার মনে হয় থার্সডে সন্ধ্যা থেকে শুরু করি, যতক্ষণ সময় লাগে। সন্ধ্যা 6:30 থেকে শুরু করলে
স্যার
রাত 11টা পর্যন্ত নেওয়া যায়।
আমাদের কি স্লাইড বানানো লাগবে এন্ড অলসো রিপোর্ট বানানো লাগবে?
এটা হচ্ছে তোমার প্রজেক্ট ডেমনস্ট্রেশন করতে হবে। আমরা যেটা এক্সপেক্ট করতেছি সেটা হচ্ছে তোমার এক্সপেক্ট করতেছি যে তুমি তোমার সরাসরি হচ্ছে কোডিং যেখান থেকে করছো সেখান থেকে এক্সপ্লেইন করবে আর কি। আর আমাদেরকে হচ্ছে সাবমিট করতে হবে একটা হচ্ছে রিপোর্ট আকারে। তুমি সেখানে হচ্ছে তুমি রিপোর্টে যে কোনো ফরম্যাট ফলো করতে পারো আর কি, আইটিপলি ফরম্যাট যেটা আছে, অথবা তুমি নিজের ফরম্যাট তৈরি করতে পারো। টোটাল কাজটাকে, যে তোমার কাজটা কি টাইটেল দিলা সেটার সেটা একটা ইন্ট্রোডাকশন লিখলাম, রেজাল্ট যেটা রেজাল্ট অ্যানালাইসিস করে তুমি কি পাইছো সেটা লিখলাম, এরকম।
স্যার আমাদের প্রজেক্টে কত মার্কস থাকবে?
আমরা যেটা ডিফাইন করছি, আমার মনে হয় যে একেবারে শুরুতে দেখো, মানে আমার মুখস্থ নাই এটা, তুমি জাস্ট ওই কোর্স আউটলাইনটা যেটা ছিল ওখানে প্রজেক্ট কত দেয়া আছে সেটা দেখো, ওটাই ফলো হবে।
স্যার রিপোর্টটা পিডিএফ ফাইলে দিলে হবে না?
হ্যাঁ, পিডিএফ ফাইলে দিলে হবে।
স্যার ফাইনালের কোশ্চেন কিরকম থাকবে স্যার?
ফাইনালের কোশ্চেন আমাদের হচ্ছে টোটাল 30 মার্কসের হতে পারে। 30 মার্কসের কোশ্চেনে আমাদের মিড টার্মের কোশ্চেন যেরকম ছিল ওরকমই হবে। দ্যাট মিনস ডেটা সেট ম্যাক্সিমাম হয়তো দেয়া থাকবে, থিওরি কম থাকবে।
স্যার ফাইনালের সিলেবাসটা কি?
স্যার টোটাল সিলেবাসটা একটু একটা অ্যানাউন্সমেন্ট।
হ্যাঁ, ওইটা আমরা অ্যানাউন্সমেন্ট করব। আশা করি তোমরা জানো যে মিড টার্মের পরে কি কি টপিকস কভার হচ্ছে সেগুলোই। তো অবশ্যই তোমরা হচ্ছে অ্যানাউন্সমেন্ট পাবা, এবং হচ্ছে কোন টপিকস থাকবে সেটা তো আমি লিখে দিবই, ঠিক না?
স্যার আমাদের টিল নাও মার্কসের ব্রেকডাউনটা যদি দেখতে পারতাম বেটার হতো, মিড পর্যন্ত অ্যাসাইনমেন্ট কুইজেস।
ব্রেকডাউন মানে হচ্ছে তুমি সব মার্কস গুলো একসাথে দেখতে চাচ্ছ, তাই তো?
জি স্যার।
আচ্ছা, আমরা কি কোনো পেন্ডিং আছে কোনো মার্কস আমাদের?
স্যার লাস্ট কুইজের মার্কসটা দেওয়া হয়নি, এরপর হচ্ছে স্যার অ্যাসাইনমেন্টের মার্কসটাও দেওয়া হয়নি।
আচ্ছা, অ্যাসাইনমেন্ট যেটা আমাদের হচ্ছে ডেটা ক্যাম অ্যাসাইনমেন্ট ছিল। ওকে,
জি
ঠিক
স্যার।
আছে, এটা পেয়ে যাবা।
স্যার ডেটা ক্যাম্পে অ্যাসাইনমেন্ট স্যার কমপ্লিট করলেই স্যার ফুল মার্কস পাবো না?
কমপ্লিট করলে তোমার হচ্ছে এক্সপি, যেটা কমপ্লিট এক্সপি পাইতে হবে, মানে এক্সপি ফুল পেতে হবে আর কি তোমাকে।
আর স্যার আপনার কি কোনো কনসালটেশন টাইম পাওয়া যাবে এর মধ্যে?
হ্যাঁ, যেটা দেয়া আছে ওটাই কনসালটেশন আওয়ারে, আমার রুটিনে যেটা দেয়া আছে।
ওকে স্যার,
প্রজেক্টটি কি গ্রুপের 3জনই মানে প্রেজেন্ট করতে হবে পার্ট বাই পার্ট এরকম?
ইউজুয়ালি তো তাই করতে হয়, ঠিক না? তোমার পার্টটা তুমি প্রেজেন্ট করবা, তুমি যেটুকু করছো, গ্রুপ ওয়ার্ক যেহেতু।
ওকে স্যার।
ওকে, ঠিক
স্যার
আছে, তাহলে আমি
মেকআপ
কিছু
মিড
অ্যানাউন্সমেন্ট
টার্ম,
দিয়ে দিব। হ্যাঁ বলো।
স্যার মেকআপ মিড টার্মের কোনো অ্যানাউন্সমেন্ট আসে নাই তো এখন।
এই উইকে মেকআপ হবে, ওয়েডনেসডে তে হওয়ার সম্ভাবনা বেশি। হ্যাঁ,
ওকে স্যার।
স্যার প্রজেক্টে কি র ইমেজেস অথবা সিএসভি ফাইল ইউজ করে মডেল রান অথবা এরকম কিছু করতে হবে স্যার?
Data যেটা data set, it can be image, it can be text, it can be signals, no problem.
ওকে স্যার, থ্যাংক ইউ।
ওকে, ভালো থাকো সবাই, বাই।
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম
আসসালামু
আসসালাম।
আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম। ওয়ালাইকুম আসসালাম।
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম।
আসসালামু আলাইকুম স্যার, একটা কোয়েশ্চেন ছিল।
হ্যাঁ হ্যাঁ, বলো।
স্যার, আমি এখনো কোনো গ্রুপে অ্যাসাইন হতে পারিনি স্যার, তো আমি কিভাবে এটা প্রজেক্টে কন্ট্রিবিউট করবো
ইন্ডিভিজুয়ালি
স্যার?
করতে পারো, ইন্ডিভিজুয়ালি করতে পারো।
সরি স্যার, আপনার কথাটা বোঝা যায়নি।
ইন্ডিভিজুয়ালি করতে পারো, মানে একা একা করতে পারো।
ওকে ওকে, ঠিক আছে, থ্যাংক ইউ স্যার।
আচ্ছা।
স্যার আসসালামু আলাইকুম স্যার। স্যার একটা কোয়েশ্চেন ছিল।
হ্যাঁ,
স্যার আমি স্যার সিক ছিলাম, এই জন্য অ্যাসাইনমেন্টটা ইন টাইমে সাবমিট করতে
বলো।
পারিনি। স্যার আমি সিক ছিলাম, এই
হ্যাঁ,
কারণে
বুঝিনি।
অ্যাসাইনমেন্টটা ইন টাইমে সাবমিট করতে পারিনি স্যার। আমি কি সাবমিট করতে পারবো আবার স্যার?
খুব দ্রুত সাবমিট করে ফেলো, কারণ অ্যাসাইনমেন্টের মার্কস তো আমাকে অ্যানাউন্স করতে হবে আর কি।
জি জি স্যার, জাস্ট এক্সপি গুলো কমপ্লিট করে ফেললেই তো হবে।
হ্যাঁ।
জি থ্যাংক ইউ স্যার। আসসালামু আলাইকুম।
ওকে।